Welcome back to the Deep Dive. Today, we are opening up a topic that seems, well, deceptively simple. What happens when you mix two different things together?
It turns out the rules governing that simple act, creating a solution, are actually the foundational building blocks of physics, environmental science, and even human biology.
We're doing a deep dive into the secret life of chemical solutions.
It's an area of chemistry, often called physical chemistry, that takes these fundamental concepts and applies math to predict behavior. I mean, everything from how ice melts on your driveway to how your kidneys filter waste. It's all governed by this one set of rules.
And our mission today is to give you a quick but really thorough understanding of all of this, from the energy that makes things mix spontaneously right up to the surprising and sometimes dramatic effect of dissolved particles on things like freezing points and living cells.
So let's set the foundation. The source material defines a solution as a homogeneous mixture of two or more substances.
That word homogeneous is the key.
Right. It's absolutely critical. It means that if you look at the mixture, you can't distinguish the parts. You can see right through it. And the composition is totally uniform.
And in that mix, you have two roles. There's the solute, which is the substance getting dissolved.
And the solvent, which is the substance doing the dissolving. And most of the time, we're talking about solutions where water is the solvent.
An aqueous solution.
Exactly. Water's unique chemistry makes it this near universal solvent. It's really the star player in almost every reaction we care about.
Okay, let's unpack this a bit. Why does mixing even happen? I mean, if I drop sugar into my tea, I stir it to speed it up. But what's the fundamental natural drive for those molecules to mix in the first place?
The drive is, well, it's baked into the nature of the universe.
Yep.
Spontaneity. The formation of solutions is almost always a spontaneous process.
So it wants to happen on its own.
Precisely. The system is fundamentally seeking its lowest possible stress state, which is a balance between achieving low energy and reaching high entropy.
And high entropy is just maximum messiness, maximum randomness.
That's a perfect way to put it. Nature loves chaos. So mixing two separate pure things into one big, messy solution always increases the entropy. But you can't ignore the energy part.
Right, because to mix things, you have to break bonds first. You have to pull the solute molecules apart from each other and pull the solvent molecules apart. And that has to cost energy.
It absolutely does. It's an energy trade-off. First, you have that initial separation you mentioned, breaking solute-solute and solvent interactions. That requires energy. It's an endothermic cost.
But then you get a payoff.
You do.
Yeah.
The reward is forming the new, strong solvent-solute bonds, and that process releases energy. That's your exothermic release.
So whether the solution feels hot or cold just depends on which of those is bigger.
Exactly. If the cost to break the old bonds is greater than the energy you get back from making new ones, you have an endothermic formation. The beaker will actually feel cold.
And if the energy released is greater.
Then it's an exothermic formation, and the beaker will feel hot.
But wait, I have a question. If a process is endothermic, meaning it costs net energy, why would it still happen spontaneously? Isn't that a paradox?
That is the key insight. You'd think it wouldn't happen. But the drive for high entropy, that desire for maximum randomness, is so overwhelming that it can actually overcome a mild energy cost.
So the chaos wins.
The chaos wins. The solution forms because the huge gain in entropy more than makes up for the small energy debt.
That's fascinating.
Yeah.
Now, how a solute actually behaves in water really depends on what it is. I know chemists draw a sharp line between covalent and ionic compounds here.
They do. Covalent compounds, think simple molecules like sugar or ethanol, they stay intact. They disperse, but they stay as one unit. But ionic compounds like table salt, they do something totally different. They dissociate their ions.
They just break apart.
Completely apart. The crystal structure shatters into individual charged atoms floating around.
When those charged ions are loose, the water molecules swarm them in a process called hydration.
Yes, and water is like the ultimate little magnet for this. You know, the oxygen end is slightly negative and the hydrogen ends are slightly positive.
It's polar.
Right. And that polarity allows water to physically rip the ionic crystal apart. The negative oxygen ends surround a positive ion, and the positive hydrogen ends surround a negative ion, creating this stable little cage of water. It's why salt dissolves so well.
It's amazing that such subtle forces dictate so much. So let's dig into those forces, the IMFs. What's the hierarchy of attraction we're dealing with?
Well, these intermolecular forces, or IMFs, they dictate that famous rule, like dissolves like.
Okay.
At the very top of the strength list are forces with full charges, ionic forces, which is ion to ion, and ion dipole forces. That's the powerful one between an ion and a polar molecule like water.
Then you move down to molecules that have partial charges, which gives you dipole interaction.
And a really important special case of that is hydrogen bonding.
Mhm.
It's just an extremely strong type of dipole force that happens when hydrogen is bonded to fluorine, oxygen, or nitrogen. It's what makes water so special.
And then way down at the bottom, you have the force that lets something like oil dissolve in another oil, dispersion forces.
Right. Dispersion forces are in all molecules, but they're the only force in nonpolar molecules. They're just these temporary random shifts in electron clouds. They're weak, but it's all nonpolar molecules have.
I remember reading about a weird one, the dipole-induced dipole interaction. Can a polar molecule actually bully a nonpolar one into becoming polar for a second?
That's a great way to put it. Yes, that's exactly what happens. The polar molecule has such a strong, persistent partial charge that it distorts the electron cloud of a nearby nonpolar molecule, inducing a temporary dipole. It allows for some limited mixing where you wouldn't expect it.
This idea of dissociation breaking apart versus staying intact, it feels like it's the key to everything that comes next.
It is the absolute linchpin. Electrolytes are those ionic compounds that dissociate completely, making multiple particles. But non-electrolytes, like sugar, they don't dissociate. One molecule dissolved gives you just one particle.
Okay, so we know how things dissolve. The next logical question is, how much can dissolve? Let's talk about limits.
Right. We define that limit with the term solubility. The maximum amount of a solute you can dissolve in a solvent under specific conditions.
And that gives us those three states we always hear about. Unsaturated, saturated, and the weird one, supersaturated.
Yep. An unsaturated solution can still dissolve more salt. A saturated solution is full, add any more, and it just sinks to the bottom.
And supersaturated.
That's the unstable one. It holds more solute than it should, usually because you dissolved it hot and cooled it down very carefully. If you so much as breathe on it, all the extra solute can crystallize out instantly.
And solubility depends heavily on things like temperature and pressure.
For salts, the rule is pretty simple. Solubility generally increases as temperature increases. Hot water can hold more dissolved salt than cold water.
But for gases, it's the exact opposite, right? That's why warm soda is so flat.
Correct. The solubility of gases in water decreases with increasing temperature. Warmer water means the gas molecules have more energy to escape. It's actually a huge problem for fish, since warmer lakes hold less dissolved oxygen.
But you can force more gas into water using pressure.
You can. The solubility of a gas in water increases with increasing pressure. That's a soda bottle. They use high pressure to force all that carbon dioxide into the liquid.
And there's an actual formula for that relationship, isn't there? Henry's law.
There is. Henry's law is mathematically simple but really important. It just says the amount of gas you can dissolve is directly proportional to the partial pressure of that gas above the liquid.
The formula is KH/CHS.
Exactly. Partial pressure equals the Henry's law, constant times the concentration. Double the pressure, you double the amount of dissolved gas. This isn't just theory, it's why scuba divers have to be so careful coming up.
To avoid the bends.
To avoid the bends, if they rise too fast, the pressure drops, and the nitrogen gas literally boils out of their blood.
Okay, so we have the qualitative rules, now we need to get quantitative. We need to describe exactly how much solute is in the solvent.
Right, and for that we use concentration functions. The most common one is molarity, capital M, which is moles of solute per liter of the total solution.
But for this unit, its lesser-known cousin, molality, lowercase m, is actually more important. That's moles of solute per kilogram of the solvent. Why the difference?
That is a crucial point. Temperature changes, right? And when temperature changes, the volume of a solution can expand or contract. So molarity can change.
But mass doesn't change with temperature.
Mass doesn't change. So molality gives you a temperature-independent concentration, which makes it far more reliable for predicting physical properties.
Okay, so once we know the concentration, we unlock the most fascinating part of this unit, the colligative properties.
This is the big takeaway. Colligative properties are properties of the solvent that change based only on the number of solute particles you add. It doesn't matter what the particles are.
Wait, really? So salt or sugar, if you put in the same number of individual particles, the effect on the water is the same.
It's exactly the same. The four key colligative properties are vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure.
And this is where that electrolyte distinction becomes so important. We need to count the particles using the Van 't Hoff factor per dollars.
Right. It's just the number of particles produced per mole of solute. For sugar, a non-electrolyte, I weigh is 1,1. But for lithium chloride, UaCl, it breaks into 2 ions, so I weigh 2,2.
And for something like cobalt chloride, chloride, it would be 3. 1 cobalt and 2 chlorides.
You got it. I weigh $3,000. So a solution of cobalt chloride has triple the effect on the boiling point as a solution of sugar at the same concentration.
That's a huge difference.
A huge difference. And we have to include that Dollar factor in the formulas. The change in freezing point is delta TF iceto O, KF dito CDA AFM. And for boiling point, it's delta TB iceto Tito MA. The change is directly proportional to the particle count and the molality.
And this is real-world stuff. This is why we put antifreeze in a car's radiator. We're deliberately elevating the boiling point and depressing the freezing point.
And it's why we put salt on icy roads. The salt particles get in the way of the water molecules trying to form ice, which forces the freezing point way down.
What about that first one, the lowering of vapor pressure?
That's described by Raoult's law. Just picture the surface of the water. Vapor pressure is caused by water molecules escaping into the air. If you add solute particles, they just get in the way.
They're like little roadblocks on the surface.
Exactly. They physically block some of the water from escaping, which lowers the vapor pressure. It's a really important principle for things like distillation.
If we connect all this to the bigger picture, I know one of these properties governs basically all of biology. Osmosis.
It really does. Osmosis is the flow of a solvent, usually water, across a semi-permeable membrane.
Like a cell wall.
Like a cell wall. And the key is the direction of flow. Water always moves from an area of low solute concentration to an area of high solute concentration. It's trying to even things out.
And the pressure you'd need to apply to physically stop that flow is the osmotic pressure.
Right. And the formula is IMRTA. Again, that particle count, $1 is right there in the formula.
This isn't abstract. This is life and death for every cell in your body.
Absolutely. Think about a red blood cell. If you put it in a hypotonic solution, that's a solution with a lower concentration outside the cell than inside.
Water's going to rush in.
It rushes in to try and dilute the inside of the cell, causing it to swell up and even burst.
And the opposite would be a hypertonic solution, like seawater.
Exactly. Much higher concentration outside, so water rushes out of the cell, causing it to shrivel up and die. This is why dehydration is so dangerous.
And the goal is an isotonic solution, where the concentration inside and out is perfectly balanced.
That's what a saline IV is. It's a perfectly balanced isotonic solution to rehydrate you safely.
So what about mixtures that aren't perfectly clear? Not everything is a true solution.
That brings us to colloidal suspensions. These are heterogeneous mixtures, but the particles are small enough that they don't settle out. They stay dispersed and they scatter light, which is why things like milk or fog look cloudy.
And within that world of colloids, you find one of the most useful structures ever, the micelle.
Micelles are amazing. They form when you have molecules that are amphipathic. It's a great word. It just means they have a dual nature.
One end loves water and the other end hates it.
Exactly. A hydrophilic, water-loving head and a hydrophobic, water-hating tail. That dual nature is what makes soap work.
To get rid of grease and oil, which are nonpolar?
It's a brilliant solution. The nonpolar, water-hating tails of the soap molecules all dive into the nonpolar grease surrounding it. They form this little sphere called a micelle with the grease trapped inside.
And the water-loving heads are all on the outside.
All on the outside, facing the water. This makes the entire sphere grease and all water-soluble, so the water can just wash it away.
It's incredible. We started with a simple question of mixing and found this thermodynamic engine driving it all. We identified the forces, and we learned that just knowing that simple particle count, the Van't Hoff factor, is the key to predicting everything.
It really is. And to bring it back to that energy trade-off, we learned dissolution can be endothermic, making things cold, or exothermic, making them hot. So this raises a final question for you to think about. If we know that dissolving certain salts can cause an instant temperature drop or an instant heat release, what practical common application depends critically on managing that enthalpy balance of dissolution, and what industrial compound is most famously used to create that temperature shift on demand?
Something to mull over. Thank you for joining us for this deep dive into the structure and power of chemical solutions. We'll talk to you soon.